All right, 7 to 5, ready to go?
I'll make the announcement, buddy.
Okay. Hey guys, welcome to workshop 3. I'm just making a short announcement before Sam gets going on the workshop. So we have a lot of our board members and mentors graduating at the end of spring. So we're going to be opening up like positions and stuff. So if anybody is interested, just keep a lookout for an announcement that we're going to be making over email. There'll be interviews and all that kind of stuff, but you can actually join the team, which is fun. So let us know if you have any questions on it. We don't have too many details at the moment, but yeah, the email should be out soon. Enjoy the workshop.
All right, how's it going, guys? My name is Sam, and I'll be doing the Machine Learning 3 workshop number 3. And yeah, don't worry about it if you haven't attended the previous ones. Just because it's the third one in the series doesn't really mean that you should have attended the first 2 ones to be able to get anything done over here. So is there anybody who has not downloaded the dataset yet? Okay. So yeah, if you haven't, just go to this link and download the folder. And it'll have 2 files, a Python file and a CSV file. And just download them to your computer. And just make sure you know where they are because you're going to need to be uploading it pretty soon. Did you get the link?
When you download the helper file, Chrome says this type of file can on your computer.
It won't. I promise you that. just do it anyway. Okay. So if you already have the link, I'm just going to move on. All right. So once you have the file, so we will be kind of using Google Colab. So just go to your, so you should be using Google Chrome because Google Colab only works well with Chrome. So if you don't have Chrome, just download it and just go to Google Colab. And yeah, just click on the first link and it should bring you over here, and then you can just go to new Python 3 notebook.
What should we call this one? It would be nice to give it a specific name.
The what?
What should we title this?
Oh, you can tell, it doesn't matter. You can tell it something, nothing, whatever you want.
Well, what are we going to talk about?
Oh, we're going to be talking about, just write down ensemble, because we're going to be doing a random forest today.
Random forest.
So you can do that. Yeah. It's not all about random forest, but yeah. So yeah, also you're going to need to be logged into your Google account for this. For some reason, you can't really open a notebook if you're not logged into your Google account. So you can do that. Once you do that, it'll bring you to something like this. And so now this is where we can upload our files. So just go over here, go to files, and I'm going to upload them with you. So just upload, and it should bring you. So just make sure you know where they are. So like for me, I was there, so I'm just going to upload both these files. They're ML3 helper and the telecomchurn.csv. So once you upload them, you should see them over here. So when you see them over here, if not, then just ask for one of those. So yeah, so if you have any questions and you're having trouble with someone, we have 2 mentors over there. So just don't be shy, raise your hand, and they'll be able to help you out there. And yeah, as soon as you see those files over here, you're good to go. You can close this off.
So the data sets that we are working on is ensemble methods.
Yeah.
Is it the same data set?
It is the same data set I've used in the first one, right? Okay. But I didn't use ensemble methods on it. I used like the simple model. So now we're going to be going in and using ensemble methods on the same data set. You don't have to attend like the first one to do this again. So let's just you're starting fresh again. I'm going to be doing all the steps over again. Yeah. All right. So another thing that you should do is just go to just go to edit and notebook settings and make sure that the hardware accelerator you're on GPU because we will be training models and we will be doing some hyperparameter tuning, which can get really computationally expensive. So GPU would help you get it done faster. Just go over here, save, and if you want, all right. Let's see. So tell me, is this? So they just introduced a dark mode, and I don't know if it looks good or not. But do you think this is better? You guys, think this looks better?
Where did you go?
So just go to Tools, Preferences, and there's a dark light theme.
So in Google Chrome, you have the option of using hardware acceleration.
Yeah, you want me to go with that again?
No. So we're using GPU acceleration on Google Colab.
What do I think? It is.
Is there any advantage to turning on or off hardware acceleration in Google Chrome?
if your computer, because you're using a GPU instead of CPU, so it will be faster. Because unless you're using like the, but for me, if I do the computation on my own machine, it's going to be CPU, right? But I'm using GPU for that.
Is there some advantage to outsourcing a lot of this computation to like Jupyter Notebooks or Google Colabs when you are?
It can make your training faster, but like this is a free instance, so I don't know how much more effective it is. But if you're actually working with something like, like Amazon and using their EC2 instances with GPU, it'll make it much faster. But I don't know about this one, so because But yeah, so let's get started.
Can you use light actually? Because I think it's better for the visibility.
Okay, sure, I'll do that. I gotta turn it back. All right. So first, we're just gonna import all the libraries we're gonna need. And just going to read in the data we have. Should be better. All right, so to quickly reiterate, kind of go over what the data set is about. This is a data set that contains information about customers from a telecom company. And what you see over here, this is information about each individual customer. This is the set of information that we have, like customer ID, what gender they are, if they're senior citizen or not, if they have a partner, dependents, blah, blah, blah. And our variable of interest over here is churn. So churn is defined as when a customer leaves your company, right? And that is our variable of interest. And our goal today is to be able to train a model that will allow you to kind of use all this information that you have about the customer to predict with some accuracy if they're going to leave your company or not. So that's our goal over here today. And this is an example of supervised machine learning problem because we know what we predict in churn. Okay, so if you want to take a look at some of the first few rows, so there's about 7,000 rows or information essentially about 7,000 customers. So just kind of look at the first few rows. Just going to use this command. Right, so this is just like some of the information that you can it's just a method of way to see your data set, the first few rows, like as you can see, right? So yeah, you see like a mixed bag of variables. Yes, no, 1, 2, numerical, non-numerical, and this is important because before machine learning, we kind of deal with them differently. So you'll see when you kind of get to it. Yeah, just gonna write this code.
Sorry, I'm having the same problem you just had a second ago, where we couldn't import telecom.csv.
You having some trouble with it?
Yeah.
Ryan, could you help him?
So I have pretty much outside okay, I uploaded telecom trend. So you see this file is being commented using instructions using the file and put it into this variable. So now this is the same thing as well. So I have two copies because we use this file on the
So I just kind of, so one of the columns that whether the person is seated in or not, it has values 0 and 1. Right now I'm just changing them to no and yes. If it's 0, that means they're not. And yes, I'm doing that only because I'm going to visualize this data, so it helps with that. But if you want, when we put our data into the machine learning algorithm, it's actually going to be have to like that. It's actually going to be have to be 0 and 1 instead of yes or no, because the machine learning algorithm, like, uses math, so it will need numbers and not like numeric string. All right. So now we're going to go ahead and like import the helper function file that we have on our computers. What is going on here? Hold on. Okay. Right, so yeah, so this file over here that you just have on your computer, I'm just going to import it into our notebook so we can use it. So I wrote a bunch of helper functions that will help us. Yeah.
So are all these methods like info and head and
Yeah.
are they all provided by pandas?
They're pandas, they're not mine, right? So any of the functions that are given us today are going to start with help or dot. Those are my functions, and you're going to have those functions on your file because they have them on your computer. I also annotated them as much as possible, so you can kind of go back and look at it. But they're kind of tedious, and I didn't want to do it over here because I wanted to take away what they do and not exactly how they do. You can figure that out on your own. Yeah. So anything that doesn't start with helper is not my function. It's from pandas. Yeah.
Can you go back to the download link? I think some people are missing the link.
The download link?
Yeah.
Oh, okay. Yeah. Let's see.
I'll write on the board. Does everybody else have this? Because you will be kind of doing without the file.
Okay. So everybody good? Jason, is everybody good?
I think so. Yeah, we're good.
All right.
So this
Right, so these are just like, so the help, if you call help on any module, it just gives you the functions we have. This is functions I wrote. Just kind of like a list of names of the functions we can be using. I'll explain them as I go as much as I can. Without dwelling too much into the details because you can read them. I annotated them for you. All right, so the first thing I want to do is just looking at this data set. It doesn't really give me a lot of information. It's just like that of what may or may not be a good feature or a good piece of information to predict whether the customer is leaving or not. So usually you just want to kind of look at your data set. You want to visualize it to give yourself how like the features are distributed, right? And how let's say for here I want to see do men over here. Let's say I have gender, right? So I want to figure out. Yeah, so I want to figure out are men more likely to churn than their female counterparts? Just looking at the data like that doesn't give me that information, right? So I'm going to visualize this in a meaningful way. And yeah, so I'm just going to write that code here using some of my helper functions. And so kind of go back over here. So most of these columns that had yes or no values, like gender, senior citizen, partner, dependents, these are called categorical variables because they don't take a numeric value. They take yes, no, or other variables. And numeric variables are the ones like over here we have tenure. Tenure is basically how long the customer has been with the company in months. So that's numeric. 2 months, 3 months, 4 months, 6 months, right? Same thing as monthly charges, like in dollars. That's numeric. So the thing is we usually have to visualize categorical variables and numerical variables differently. So I'm going to start with just the categorical variables. Most of the data set is categorical variables. So I'm going to visualize categorical variables for you right now.
These should probably, that's probably
in a second. Can you go back up to line 5 real quick?
Line 5?
Yeah.
Yeah.
Oh, you're looking for
It has some metrics.
so it's a curly brace.
The senior citizen knows.
You're good.
It's capital on skills.
Yeah, you're good.
All right.
And then the value is so what exactly are you sure you can? That's what
Oh, you called it telecom. Telecom, not
Right, so just to show you an example of what just happened right now is using the helper function, I basically grouped each categorical variable into its own little data frame to kind of show me the percentages, right? So over here, if you look at this, I mean, yeah, you can go back again. So any helper function I use has been really well annotated, so you can go back and look at how it's done. But basically, now I have the percentages at the proportion at which like the values in this categorical variable like kind of like distribute the target variable churn. So over here you can see that men and women kind of like churn at the same rate. It's about 26% for both of them, right? And right now you can only see one data set, but I've done that for every category of variable. And now when I visualize it right now with another helper function, you'll be able to see the whole thing on your on your machine. Right, so let's just. Yeah, also just a quick tip, you can also press tab if you're writing a function or something like helper dot, so it'll just give you a list of everything so you don't have to type all of it out. So like over here, like if I go back here and just press tab, it just gives me something to choose from so you don't have to write it all out. All right, so this works. Just gonna full screen this for you. All right, so now I can actually see with this bar graph like the proportion, like how likely the value, like how they differ, how likely it's like, let's say over here when you look at first one, you have male and female, and the red part is like, so this is a proportion, this is 100%, so it's in percentages, not raw values, right? So you see on the top, because like you have 80% who have not churned and 74% that have not churned and 26% that have churned from the top, right? So this kind of helps you like visualize how like what the proportions are for like how customers are leaving. So when you look at this female and male one, they kind of churn at the same rate. So chances are this variable is probably not going to provide you a lot of information when you're actually making a prediction because they're the same thing, right? In contrast, now contrast that with something like this, right? Let's look at this, right? So this feature is called internet service. What kind of internet service you have, the customer has, and you can clearly see that the customer's fiber optic churn at a higher proportion than everybody else over here. So this is more likely an important thing to know for the model when they make a prediction. They're probably going to use this and give it a lot of weight. Because you can see we have differences in all the values of this feature. Right? If you just had this information and I gave you 3 people, one of them had fiber optic, or one of them had DSL, no internet service and fiber optic, and just like frequent this probability and ask you who's most likely to leave, the answer would be fiber optic right here. Because they churn, as you can see, the probability of them churning is higher. They churn high proportions. So yeah, so this is just a way to kind of like, so you can't just look at a data set and you're going to figure this out. So that's why you need to visualize this stuff to kind of like give you an idea of how your features are distributed. Right, same thing over here, you go down over here. And same thing for like, this is payment method, right? So you can see people who actually pay by electronic check have a higher proportion of churn. They leave at a higher rate than everybody else. Mail check, credit card, bank transfer, right? So okay, so these were all of our categorical variables. Now I'm going to see the distribution. I'm going to do the same thing. But
I think we need to go to line 6 if you can.
Yeah,
If you do
for sure.
Okay,
Yeah. All right, so now I'm going to do the same thing for the numerical variables, right? So I got all the categorical. So my two numerical variables are tenure, which is in months. Like, so this is like how many months the customer has been with us. Either they're already like, like if the person has left, so how many months they were before they left, or like they're continuing how many months they have been here. And the second one is monthly charges. I'm going to look at the distribution of like monthly charges for both the people who left and who did not leave to kind of show me distribution differences in there. So let's get that going. Last line for this one?
Right there.
Okay. I'll wait for you. It's okay.
So I'm still doing that.
Are you still in that?
Block 6, was that help helper?
Yeah.
So what's like the main thing that the categorical segment does?
The main thing that
The categorical segment, like what does it do?
categorical segment.
Yeah.
So like it takes all the categorical variables in your data set and then counts how many values for each value in that categorical segment. So like I had a categorical variable called gender. It had two values, male and female. So essentially it says how many male values total exist in the data set on female. Then it goes and sees how many of them left or did not leave, and then calculates the proportion.
Okay.
Perfect. So this is a group by operation, a pretty common data set manipulation operation that you can do in SQL or Python. And Pandas makes it really easy to do that. So yeah, again, the code in the helper function is code from the Pandas data frame, from the Pandas library, right? So I didn't write all this myself. I just kind of like put it all together, composed it in the helper functions. So again, I annotated them very well. So if you go to your Python file, you'll be able to see all these functions and what they do, right? And then you can go to the Pandas the documentation, and you'll be able to figure it out, right? All right, let's get moving. All right, let's do that for the continuous variables. So when you're able to do that, you'll kind of see something like this. So this is like the distribution of my, the first one is monthly charges, right? So the blue one is the people who are still there, and the green is the people who left, right? So you can see that monthly charges are distributed differently for both of them, right? So when you look at the people who are kind of retained, you see that most, like, look at the peak. The peak is around like $20, right? That's a low peak. So this side, there's no peak over there, right? The peak is kind of like over here. People who churn are usually people who churn, like, who pay higher, like, have a higher monthly cost, they leave, which is kind of like reforms your intuition about it, right? People who leave probably pay a lot of money, and they're probably going for like better or cheaper services, right? So the good thing about this is I want these this variable to be distributed differently from my target variables, right? Because if it's distributed differently, it makes it easier for me to distinguish between them, distinguish between them. I would have a problem if they were distributed completely identically, right? Because then my model doesn't know the difference. The value is like the same across both of those targets, leave or did not leave. So that's the first one. And similarly, we have tenure. So tenure is in months, right? So for retain, it's kind of like uniform. Like you have two little peaks, like around like pretty close to like a couple of months, and then close to like more than like 70 months. And people who leave, look at the peak. This is a huge peak around like, so basically you can say that most people who leave pretty early into the service, right? If they stayed, they stayed. Right, look at the distribution. Like if you stay, you just kind of stay and maybe over there. But if you're leaving, you're probably going to leave pretty early. So let's say I was not doing any machine learning, but I was just doing some data analysis, and I'm an analyst. I'm going to be like, hey, in your company, people who leave are leaving pretty early. So pretty early, hit them with all the discounts you have. Make them a good customer. So later, they might not leave once they get used to the service. So this is good information for me. And I'm not like manually doing anything for the model. It's just I just know that this will be a good variable to kind of distinguish between stuff. Right. And so again, you can't just see that from a data set. You have to kind of make this plot. This is called a violin plot. I did not write the code for it. I imported it from a library called Seaborn. Right? So this is not something that I did and created all this. Right? I just imported some code and put the information in. Again, it's in the helper function to be able to see it. All right. Right. So now we kind of got the visualization out of the way. We're gonna move towards kind of like the machine learning, and for that, we need to do something called pre-processing our data set. So the values that exist right now in the data set, they're not fit to be just fed into a machine learning model. They can't, because you have strings, right? And the machine learning model cannot do that. It cannot process strings. It needs numbers. So we're going to pre-process them in two different ways. One of them is called binary encoding, and one of them is called one-hot encoding. So starting with binary encoding. So binary encoding is obviously for the variables that have binary values, yes or no, male, female, right? So what that means is I'm just going to take, and it's really easy and intuitive. So what I'm going to do is anywhere, and so let's say partner, I'm binary encoding that one, right? So anywhere it says yes, I'm going to put a 1 there. Anywhere it says no, I'm going to put a 0 there. That's it. I'm going to add numbers to distinguish between them, right? That's how I encode something for machine learning. And one-hot encoding follows the same principle, but it's done for, so it's kind of done for variables that have more than 2 values, because if they don't have 2 values, I can't binary encode. I have to figure out a different way. So what I do so look at this variable, right? Internet service. It has 3 values. It has DSL, fiber optic, and no. So what I'm going to do is this is one column. It has a bunch of values. I'm going to expand each of this value into its own column. DSL is going to have its own column. Fiber optic is going to have its own column, and no is going to have its own column. And if the value for that observation is no, both of these will have zeros, and this will have 1. So I'm going to expand it. That's how this is called one-hot encoding. You have a question? One-hot encoding.
One-hot
encoding. Yeah. I'm gonna write the function for that. So this is how you do it. And obviously, when you think about it, it's gonna your columns are gonna expand. Like you might. So let's say I only have 1 column, right? This is gonna make 3 columns. So this is how you kind of. In principle, it's the same thing. It's only 0 and 1. But you cannot encode it inside the column because you have 3 values. So you make a separate column for each of these, and put 1 in only the column. It's the value, the value is for that column. So that's called one-hot encoding, and we're going to be doing both of those because we have those kind of columns. We have columns that can only take 2 values and more than 2, and they're all categorical. Right, so let's start with the binary encoding part. So So I'm just dropping some redundant columns that they're not really any use to me. Total charges is not used to me because I have months and I have monthly charges. So, don't really need this column. And then customer ID also doesn't really provide me a lot of information. It's just a bunch of random numbers or with strings. So I'm just going to drop that from my data set because I don't need it. Let's see what we messed up over here. Weird. I'm not sure what's happening here. Actually, we can just go ahead and use so the function that's going to do the one-hot encoding first, if I use it for binary, it's going to do the same thing. It's just going to binary encode it again, so I'm just going to go ahead and use that. This function I just wanted to kind of illustrate the difference in it. But essentially, the function that does one-hot encoding can also do binary encoding. If it has two variables, it's going to do it it'll just encode it twice, right? So I'm just going to use that. Not sure what's happening if I ran it like an hour ago. It was working fine, but whatever. We're just going to get rid of that. I just change it right up here. Never mind. So yeah, this is the one-hot encoding function is not something I wrote. Fortunately for us, the pandas library provides us for that. It's called get dummies, and I'm just using that function. All Right, so that works, lucky for us, right? So here you go. So like I said, so over here you saw that we had 2 values for gender, right, male and female. And that created a column called gender male for us, right? Because I told you it's going to expand the values, it's going to make it home. And the first observation is female, that's why there's a 0 there, right? Also, another thing that one-hot encoding does is, okay, you might be thinking, where's the female column? The point is, like, after you do a one-hot encoding, you drop 1 column, right? Because if this is a 0 here, it's given the other value is going to be 1. You don't leave it in there because it's going to kind of go for double counting, and we don't want that, right? So let's say you have 3 columns, 3 values, and the first 2 are 0. Even if I don't have the last one, that means the last one must be 1. So it's not both of those. That's all the model needs to know. So yeah, if you look at this, every category we have has been expanded over here. Phone service, all those. And 0, 0, 0s over here. 1 because paperless billing was 1 for this person, everything else was 0. So this is kind of like a data that's been pre-processed. I've converted all categorical and string variables to numerical variables that still kind of provide the information that the machine learning model needs. Like, does this value exist for this person or does not exist? Right. And yeah, also we end up exploding our columns to 30 columns. So the drawback for that is that it reduces your training speed. The more columns you have, the more time it takes to kind of do any kind of computation. That's one drawback of this method. But this is like the go-to method. This is how you usually encode your variables. All right. Okay, let's import the libraries so we can do some machine learning.
Essentially, we're using built-in methods in the SK-learn to do random forest.
The what?
Rather than doing this all by hand, writing this from scratch.
I can't really hear
We're
you.
using
sklearn.
proprietary libraries from the SK-learn library
Right.
to do random forest
Right.
classification.
You said proprietary library?
Well,
It's open source. It's not proprietary. So that's the opposite of proprietary.
belonging to the SK-learn library.
Well, no, it's not. If it's open source, it belongs to everybody who gets to use it. That's the whole point of open source. You can contribute to this library. You can make this better, and you can't really make changes to something you don't have, right? That's open source. It's not proprietary. Most companies would ask you unless you're a PhD, like, what's your best option? Even if you kind of get to it and you pick up a book and you're like, I'm going to write all the math behind it. It's going to take you a while to get up to the kind of like the effectiveness this library provides you just to begin with. Right, so why do you want to reinvent the wheel? Unless you have a very specific problem that cannot be solved with this. For our problem, this solves it, right? So it'll be kind of like time consuming for me to kind of invent a solution that already exists for me, right? So that's kind of productive, right? So again, not proprietary, open source. All right, so a quick overview. Actually, I'm going to write this and I'll let you guys know.
state parameter.
Huh?
That random state equals
Sorry, what?
random state equals 21.
Oh, it's just a random seed because there's a lot of randomness involved when you train a model. It has to start with some values and train those. It's just for reproducibility. If sometimes like just because of the random seed you chose, you might get different results when you run the same algorithm on the same data. So you want to get the same results every time, so you kind of set the seed.
Is there anything special about the number 21?
No, I don't think there's anything special about that.
Is it at random?
No, it's just no. You can choose whatever number you want. You can choose any number. I just chose 21. But
I'll add to that. The random seed for the splitting thing is used as like a randomizer to split. So what he's trying to say, if you set the random seed the same every time, you'll always get the same split. So it's good if you want to try it again. If that makes any sense.
Okay. And why are we? Is there a particular reason why we're training on 20% of the data set? Is it just a convention, or?
Normally that's the convention. So 20% is normally. If you have like a large amount of data, you can kind of cut it down. But 20%, 20-80 split is normally like the standard version we go with. But it has to depend on how much information you have.
If you have a data set of like 10,000 values or something.
Yeah, that should be fine. I'd go 80-20 on that one.
all right, so let me go over some like things what we're doing here before we get into machine learning, right? So like I explained, like we have a supervised machine learning problem. That means I have some information and I'm trying to predict, I have information about the customers and I'm trying to predict if they're going to leave or not, right? So X is the information that I have about the customers, all that information. And my Y is what I'm trying to predict, churn, yes or no, 0 and 1, right? So we have to split that. So we have to split those in order to like kind of feed them into any machine learning model. The next thing, what I'm doing over here is fundamental to, I'm going to explain the problem with like machine learning model space. So a lot of times what happens is like when you train the machine learning model on certain data, what happens is it overfits on that data, which means that it learns too closely to that data. Our goal is not for our model to pick up the idiosyncrasies of that data. We want it to understand general underlying patterns, right? Because ultimately my goal is that at some point I'm going to have all these features about people, but I'm not going to know if they're going to leave or not. That's when I'm going to use my machine learning model. And that's the data I did not train on. So if my model can only recognize the data that it trained on very well, it's not going to generalize well. It's not going to do well. So to deal with that problem, when you actually to figure out how to evaluate, so in order to like effectively evaluate your model, before you train it, you break it. So you break the data set into two parts. You call one part training set and you call one part testing set. You only train the model on the training set, right? And then once it's done and you've tuned your hyperparameters, which we're going to do, then you see how well it did on data I did not see. So basically you can think of in the absence of new data, I'm stimulating new data by hiding the data I have from it, right? So that basically like if my model hasn't seen this data and I kind of like see how it does on it, that's my best guess right now how it will do in data it hasn't seen. So that's essentially why I'm splitting it. If I only test my model on the data it has already seen, I'm only testing its accuracy on the data it has seen. I cannot test its accuracy on the data it has not seen if I train with all the data I have. That's essentially why we do this train test split. Over here. What up?
So you're dropping that column because that's the one you want to predict.
So yeah, I dropped that column because the thing I train on, like, so I'm separating them. What I have, what I'm using to predict what. So I'm separating those two things, right? So yeah. So I can't have churn in my experiment because like that's the thing I'm predicting. I want my model to look at it, something it doesn't know, train it, and then see how well it kind of predicts it. And then, right, so once you have those, then you break those further, right? So you have, that's why you have X train and Y train. So those are your X and Y variables for your training set. X test and Y test, those are your X and Y variables for your test set. And 0.2 is the proportion. So that means 20% of my data is testing and 80% of my data is training. That's how usually the proportions go. You want like because in general, more data you give to a machine learning model, the better it does. That's why, depending on data you have, you're going to have like a bigger training set, right? Right. So now let's talk about the things that influence how, or like if your model is going to overfit or not, right? Those things are called hyperparameters. Hyperparameters are my parameters that my model cannot learn from the data. It is something that I have to give it in order for it to like get a good match between training and testing accuracy, which we're trying to get. And so because think of models are just like, they're like very narrow-minded. All they care about is reducing error. That's the math behind it, reduce error, right? So they don't understand the concept of like, am I overfitting to this or not? They just want to fit to it, right? So these hyperparameters is what allows us to kind of control if a model is going to overfit or not, right? So I'm going to demonstrate with that with a machine learning algorithm called k-nearest neighbors. So the way k-nearest neighbor works is like I have this data that exists in some space, right? So let's say I have a point in some point in the space, and when I say, hey, is this customer going to churn or not? It's going to look at its k nearest neighbor. So if I'm using k equal to 1, I mean it's going to look at its closest neighbor. If its closest neighbor in that space is a person who churned, that point is going to be classified as churn. If I use 2, it's going to look at the 2 closest, 3, 4, 5, right? And that's a hyperparameter. That's something that I have to tell the model before it starts training. It cannot figure out how many neighbors it should look at. Because most likely what it's going to do is only going to look at one neighbor. It's going to be like, all right, the nearest one, that's the one I'm going to be, but that's overfitting. And we're going to see that right now graphically. So before we get into ensemble methods, this is not an ensemble, this is like a basic algorithm. So I'm just going to show you guys how that'll look. And this is, yes, it's going to be a little bit of computation. Hopefully, everybody turn their instances to GPU. You just make sure that, you have GPUs over here because I can train faster. Just edit, and then notebook settings and GPU. All right, I'm going to plot this. So I'm actually going to start. So I'm going to have 50 different models. I'm going to train with 1 neighbor, 2 neighbor, 3 neighbor, 4 neighbor, all the way up to 50 to show you the training and testing accuracy. That's why it's going to take a little bit of time. All right, let's kind of go over here. All right, there you go. So get away from here. Stop. All right, so in blue I have my testing accuracy, and green I have my training accuracy across different values of how many neighbors I'm looking at, right? Okay, so look over here. When you start with 1, it starts with 1, not 0, right? Look at my training accuracy. It's almost 100%, right? And my testing accuracy, like quite low, like that's a 30 point like decrease, right? This is what overfitting looks like. Your model does really, really well on your training set, but when you give it data it hasn't seen, it just screws up completely, right? And as I increase the number of k, look, it kind of starts converging. So what we're looking for is the point they converge, where they're the closest to each other. That's the model that's not overfitted. So right over here, if you look at kind of like, you could pick a value near 20, you can pick a value near 30, and also like the lower value you pick for k, the faster it will be trained, because if you pick 30, it's looking for 30 neighbors before you can decide what that point is. So it's obviously you're going to be, it's going to take more time than versus 20. And you can't see this in this graph, but at some point if I keep increasing k, right, 50, I go to 100, 200, you'll see both of these accuracy drop down. That's called underfitting. That means my model didn't generalize at all, even for the data it was trained on, and for the data it didn't. It has seen, it has not seen. So these are the two kind of like the spectrums. You have overfitting and underfitting, and you're trying to find the sweet spot over here. So this is just kind of showing you an illustration of how a parameter can affect how your model does on some data, right? So you see over here, really bad, and then it starts converging as I increase the number of k. So again, k is a hyperparameter. My model cannot. My model is going to pick 1. If I let it pick, like, hey, what k do you want to go with? It's going to pick k, 1 because that's the one that reduces the most error, but error in what? The data it has only seen. Right? So the k is how we control how well it generalizes to new data. Right. So now the thing is that the k-nearest neighbor only has 1 hyperparameter. And so k-nearest neighbor only has 1 hyperparameter, but something like so k-nearest neighbor only has 1 parameter, so I can do it manually like I just did. But what about something like random forest? Random forest has like 8 or 9 or 4 or 5 different sets of hyperparameters, right? And just by simple product rule, if I have 4 values for 2 hyperparameters, like if I say I have maybe like 8 values for each hyperparameter that I'm going to test it on. That's 64 combinations I'm going to have to try to find the best kind of like the value. And doing it manually can get really tedious, so we do something called grid search. And we do it with something also called k-fold cross-validation. So I'm just going to explain k-fold cross-validation, what it is. Let's see over here. Right. Okay, so again, I'm talking about just the training set right now. There's a set of data called the test set, or you can call it the holdout set, that I'm not going to let my model see at all. Don't confuse that, right? This is only 80% of the data, right? Now for that 80% of data, I'm splitting it into 2 sets again. So because I want to train my hyperparameter. I want to, let's say, pick a value for k, 5, and then see how it does on some of the unseen data that I stimulated from my test set, and then 8 and 10, and kind of see how it does, right? So just forget about the 20%. This is just 80% of the data. I'm splitting it again, right? So and then seeing how well each parameter does on this kind of like when I break it up and kind of like train it over here and test it over here. The problem with this approach is that I had 80% of the data, and now I'm splitting it even further into more. So my model, and in the end, gets like really less amount of data, and the model needs like more data to kind of do well on it. And another thing why this approach is problematic is, let's say you pick this over here, you pick this segment over here. What if that segment is just, you get lucky and it just has more differentiable values, right? You get lucky and pick a good fold for your model, and the reason why some of the parameters do well on it is not because the parameters are good, because you got lucky, right? So we need a way to combat this problem, and that's when k-fold cross-validation comes in. So this is an example of 5-fold cross-validation. So what I'm going to be doing is, instead of 1 fold, I'm going to split my data into 5 folds, right? So let's say I want to test, how well this k equals to 5 does for my data set, right? So so for each iteration, so I have 5 folds. For the first iteration, I'm going to use this as the testing one, and everything else is the training one. So I see how my model does. Then for the next iteration, I'm going to pick a different fold to test, and then train on everything else, and then select over here, and like that, and again and again and again, until each fold has been used as a test set at some time. When I have all these, and when I have the performance across all the folds, I'm going to average them to see how my model does. So how does this solve the problem? My model has been trained on every piece of data because I've chosen different test sets. So it has kind of like, I've seen the performance across all of the training set because I chose different folds, and at some point the model has all of the data as training data, from which it's trained on. And if I get lucky, and if there's a fold that I got lucky on, it's not going to be the same case the next time I pick a fold, right? So this is why we use 5-fold cross-validation. Now this is kind of like it can be a little tricky to understand. So is there any questions about this? Because I know I want to move on when we kind of like at least get a good handle on it. Are there any questions about 5-fold cross-validation? Yeah.
So do you train each data value 4 times in this case?
For each data value? Yeah, so let's say I have a data set, I just divide it into 5 things, right? And when I pick, so this is my test set, I'm going to train on everything else for the first iteration.
So it's the same model as being trained on all of those?
Yeah, it's the same model, because it's the same model, so it'll be the same model with the same hyperparameter combination, right? So it'll be n is equal to 5 on this one, 5, n is equal to 5, all these will have the same parameter because that's how I compare the performance of this model, right? So if let's say I'm comparing 2 of them, so let's say I'm comparing 5 neighbors versus 10 neighbors, I'm going to train 5 neighbors on all of these, average the prediction, then train 10 neighbors on all of these, average the prediction, and then compare it. So they kind of like deal with the problems that I talked about. Yeah.
So the error is like averaged over all iterations?
Yeah, you average it. Yeah, you average it. You can even look at the standard deviation to see, because there's like, if your standard deviation is really high, because your model is doing extremely differently on both folds, there's probably some problem with the data. So you want your standard deviation to also be kind of close to each other. So that's basically 5-fold cross-validation. And obviously, again, the drawback, extremely computationally expensive, right? I'm training each hyperparameter combination 5 times, right? So let's say I have 10 different combinations of hyperparameters I'm training, that's 50 times I'm training the model to get that prediction. So it's computationally expensive. Again, if you go into the real world, you have millions and millions of rows of data, you're just going to settle with plain old train stress sometimes, or maybe like 2-fold cross-validation, something like that. Yeah, you can do 2-fold or whatever, but like, yeah, but you have less data set like we do, this is a really good way to kind of figure this out, right? So now we're gonna use an ensemble method called random forest. Random forest is a collection of decision trees. So just to reiterate what a random forest, like I talked about it last time, is just you take a bunch of decision trees and you train them all on the data. So the reason you don't train just one single one is random forests have a problem with overfitting. They overfit really easily, like we talked about, right? So they've overfit really easily on the data. So instead of having just one, you train like 100, 200 data set and you average their prediction to what's it. If like, let's say you take a vote, let's say like 80 of them say that this is like a person who's gonna leave, so the model predicts it's gonna leave. Because it has a bunch of different hyperparameter combinations, not just one, we're going to use something called grid search. It kind of deals with all their values for us. We don't have to like manually input that code, write a bunch of for loops to get that done for us. So it'll become clearer, and I'll go over what the parameter is or is not. All right. Let's instantiate a model. So n estimators is how many decision trees are in this random forest. I'm starting with a very low number because I'm about to do k-fold cross-validation on it. So I want to keep I don't want to have a lot of trees because it'll make the computation even slower, right? So I just want to do that. Also, so the one fundamental thing about random forest is that each tree is not going to have all the data in it when it trains it. Each tree usually only has 1/3 of the data set. So it's randomly going to pick 1/3 of the observations from the data set and train each tree. So again, this also helps to combat overfitting. And then max features is basically not just the observations, but also the columns, right? So let's say one decision tree is only going to deal with 1/3 of the data set, and it's not even going to have all these features. It's only going to have like a subset of these. Right, so the reason why we do that is because, again, we don't want any of the decision trees to overfit on the data. So we only give individually, we give them a little bit of information. So combined, they can make a good prediction. That's not overfitted on the data. So max feature is basically is saying that if I have 9 features, the value for this is square root, then each tree is only going to train on 3 features. I'm just taking the square root of the total. So that's it. All right, so instead of kind of going over what exactly each hyperparameter is, because it can get tedious, I mean, you can always, because you have the code, you can always go back and look at the documentation for this and figure out what it is. But all you need to understand is in some way or the other, it's helping us combat overfitting. It's trying to give us the best metrics possible, right? So if I just quickly go over min sample split, it means minimum number of samples in a leaf that the tree must have to split it further, right? So a lower value would make it overfit, and a higher value would make it not overfit. So so in some or the other way, these parameters are helping us combat overfitting, and we're going to train a bunch of them. The exact definition, you can always look at the documentation. It'll get very tedious if we can't go over all of them. So CV, how many folds I want 5-fold cross validation. This could be 10 and 20, but if you keep increasing it, it's just going to take a lot more time. Njobs is what basically me telling this piece of code to use all the available computational power available to it right now. If I don't give it anything like a value, it'll just default is it'll just use one, the one core it has. But my negative one, I'm saying just use everything you have in this computer right now to train that model, so it'll be as fast as possible.
Sorry, and
It's just me telling the model that use all the computational power available to you right now on this computer. Not just one core, use all the core. And because we're using a GPU, so it's going to use all the GPU.
Okay, so
Yeah.
multi-thread. Multi-thread.
So is that?
Multi-core process.
Yeah, basically. You have a question?
So would you ever want to set it to some other value, or?
Yeah, depending. Maybe you have a different model running on a different core or something. You're doing something else. So yeah, definitely you would want to. But I mean, I usually just set it to like everything. So I want to get my results as fast as possible.
Have you tried running this? Have you tried running this?
I will run this, as soon as I'm done writing. I did run it, and it took a while. I mean, not a very long time, but a little longer than I would have wanted it to. But, just make sure. Okay, so what's going to happen right now is, so I have, these are my parameters, and np.arange is basically like the Python range function. Basically, so I'm telling it to give all the values from 2 to 10 and 1 to 10. So that's 9 values for the first one and 10 values for the next one. That's 90 combinations that I'm about to try. What I'm telling, so when I call fit on my data, the grid search object is going to take all these values and it's going to try every combination of the data possible using 5-fold cross-validation and tell me what the best parameter was and what the score was, right, for this data set. So in order to do that, it's going to try 90 combinations. And that's a lot of combinations. So I'm going to let it run. We're not even done with, because it has more hyperparameters that we need to tune. I didn't want to put them in the same dictionary because that'll be like 500 combinations. I don't want to do that. I'm going to split those up. But yeah, while it's running, just copy this entire cell and paste it, so we don't have to write all this again. And yeah, I'm just gonna move on and kind of like change the dictionary to handle the next hyperparameters I'm gonna be tuning. Okay, it's done. So after trying 90 different combinations using 5-fold cross-validation for each, it found that the best value for minimum sample leaf is 8. And the best value for minimum sample split is 2. And the accuracy, the highest accuracy it could achieve with those parameters, 80%. It was correct 80% of the time. Again, it is still for the test set though. When you go for a training set, it's going to be a little lower. But because we use k-fold cross-validation, we already know that the accuracy in the unseen data set is going to be close to this one, right? If we hadn't used k-fold cross-validation, we could not trust their accuracy at all. Right, so it's 80%, but it's still going to be a little lower, but not too much lower, right? So so now we have this, and now I want to tune other parameters. See, maybe I can improve that even more. So I'm going to go for I'm going to train different parameters. So for that, because the first thing I'm going to do is draw max features. Right, let's see. Right, so now the parameters I get that are doing well, I'm going to put them in here. It's minimum samples split is equals to 2. Minimum samples leaf is equals to 8. Right? So I know these are good parameters. So I'm going to put them in the model this time. And I'm going to use those to see, now I have these good values for these two. Based on these values, let's train more and see what happens with the best value for us, right? So the next one I'm going to do is max depth, which is basically how deep I want to allow each tree to go. The deeper I allow it to be, the more orphited it will be. So depth, like how many steps do I want each tree to have? And I'm also going to see what's a good value for max features. When I trained this, I already put max features as the square root, but this time I have 2 values that I can use, so I'm going to see which one is better. All right, so yeah, just make sure that you name this, like if you name this like param grid 2, you put param grid 2 over here. If you don't, it's going to run the same thing from this cell again, right? And you're just going to waste your time on computation. So make sure that if your feature, whatever your name you gave over here, param grid 2 for the things you're going to try to test out, it's the same one over here.
What did you change in parameter grid 2?
Huh?
What changes did you make to parameter grid 2?
In this one, in this cell. So I took the parameters that came out, that did well in the last cell and put them in here and see how much further I can go with this for the next parameters.
Max step.
So for this, so this cell, we're looking for a good value of max step and max features. We already have a good value for minimum sample leap and minimum sample split. So I'm going to put those in there. Right? Everybody put that in there, right?
How do you choose the ranges?
How do I choose what?
How did you choose the ranges for like max steps? Like how do you know what the
The values for that?
Yeah.
So a little bit of intuition, a little bit knowing like what max step does. So I can't choose 1,000 for max step because no tree is going to go that much. But usually, it just depends on what kind of model it is, right? So something like a hyperparameter. So it's just understanding like there's a hyperparameter called learning rate for they usually used for boosting algorithms, and that takes values like 0.001, 0.011. So one thing is understanding it, but most of it is hit and trial, right? So you want to know the appropriate range for it. Like the appropriate range could be 1 to 30, 1 to 50, right? You don't want to start with 1,000, but once you know the appropriate range, it's hit and trial. There's no set of hyperparameters that will do well on every piece of data. There will be different ones, and there's no formula for me to calculate that. The only formula is see what happens. Like use all those combinations and see what happens, right? So yeah, so just know the appropriate range, and then it's all hit and trial. That's about it. So yeah, again, so when you read the documentation, you kind of maybe you'll do it by yourself later. So you kind of figure out where max step what values you want to start on. And for this thing, this is not something I figured out. This is the only values it takes. This class, this object, max features, only takes values square root and log 2 for this. If I put anything else, it's going to give me an error. So sometimes you get lucky like that. Like the person who wrote the object restricted it. Yeah. All right, let's train this one. Just while it's working, just copy. Let's just make sure we're ready for the next one. All right. So we got value max stat 12 and max feature square root. So if you look at the results for this, both of these, right? So my max stat over here was not 12, it was something else. So my accuracy was 80.7. And over here, once I found a better value for max step, it went above. It went to 80.9, right? This is a small increase, but you're basically trying to optimize your model for the data you have. Usually in machine learning, a very high increase in like performance usually comes from either applying a different model, having more data, or better features. Hyperparameter tuning only helps you figure out overfitting, underfitting for the data you have and optimize it for the data you have. You want to see huge increases, you use a different model. Right. So now that I have a few sets of like hyperparameters that I know work for this model. So I'm gonna so if you kind of notice, I've only used the test set, right? I've only used like the training set. Only use the training set. So right now I still don't know like how my model would do on the data it has not seen at all, right? So now is the time that I have good values that I'm going to plug in and see with those values how well it does on my test set, right? So that's what I'm going to do. So a few changes I'm going to make for that is, again, like I said, I used 20 because we were training and I didn't want to use the computation power, but we're going to blow this up to 1,000. We're going to use 1,000 trees.
1,000 trees.
Yeah, we can. It's not because we're not doing any cross-validation. Again, try to understand how much computation power cross-validation will take. 90 combinations, 5-fold for each of them. You know what I'm saying? This, nothing in front of the cross-validation we just did. I could have 50,000 trees. It'll still be fine. So it's like, I'm not 50,000, but you know, I can blow this up even more. But so after a while, the accuracy can go down also. So like yeah. So first of all, it'll go up, then flatline, and at some point it'll go down, just a little bit. Okay. So max depth. I'm going to set it to the value we just got, 12, max features, square root. Where's my all right. So now I'm going to fit the model on the testing set. Oh, sorry, I'm going to fit it on the training set, and then I'm going to test it on the testing set. I never fit my model on the testing set because it's just for testing. All right, so to actually see how, so model accuracy as a metric can be a little misleading when you're actually trying to like look at how your model did. In the end, accuracy is completely fine while you're training the model, right? But once you're actually evaluating, simply accuracy can be a little misleading. So that's why we're going to use kind of like a matrix to see how a model actually did, and I'll explain it exactly how it works. And I wrote the function for it. So also, sklearn gave me the library, like gave me the functions to visualize that matrix. I just like put it in a helper function so we can use it. This is so weird. What? Yeah, this is something I didn't want to happen. Oh, got it. Sorry. All right, so I'm gonna blow this up. All right, so I'm just quickly gonna explain. So first, accuracy on unseen holdout set, right? So we had 80% on our training one and 79, right? I told you it's gonna be pretty close because we stimulated unseen data. But 79, is it good? 79%, like if you think about it, right? 79 is right. It's almost right 80% of the time. A model, like you give it a bunch of customers, it'll tell you 80% of the time it's doing well. But so from like a mathematical sense, yes, it's good. From a business sense, no. The reason for that, like let's see why. So this is what's called a confusion matrix. So we have two values that we're trying to predict, right? Retained, was the person retained, or was the person churned? Right? We have two values that we're trying to predict. So row-wise, this is the actual. So for whatever, so like we gave it a bunch. So we gave it a bunch of x, like the variables it was trying to predict on, and it predicted something they'll from us. So this is the actual class of the actual the value for the target variable, and this is what our model predicted. So essentially, on the diagonals is where you want to see like as dark as possible, and on the off diagonals you don't want to see as light as possible. So basically, this means is. So you see that when the class was retained, our model did a really good job of predicting retained. Like look at that, it's really dark. It's like close to, it's 91%, right? And when you come to the churn, the other side of that, how good was our model at predicting the people who left? You can see just from the color, it's 54%. So basically what that means is our model was really, really good at predicting people who did not leave, but it was absolutely trash at predicting the person who left, right? And why did we still get a higher accuracy? Well, that's just something called class imbalance. In my data set, most of the people were the people who did not leave. And like I said, my model was trained to do one thing, reduce error. That's all it was supposed to do, right? And what it did was exactly that. It gave it knew that just by really predicting like the majority class really well, I can get a good score. So that's what it did. That's not the model's fault. But if you look at it again, so my model was like, my model was like right for people who left. It was only right 45% of the time, not even half the time. It was absolutely and because this is a binary variable, like that's absolutely trash, and that is not a good thing. And the reason for that is not because the model is bad; it's the class imbalance that exists in the data set. This is something that machine learning models deal with like a lot, right? So if you think about something like credit card fraud, it happens very less. So when you have a data set with credit card fraud, right? You're going to have very few, let's say you have a credit card fraud and you have 5 values of credit card fraud and 95 of not, right? So if that model predicts just not fraud, it's going to be right 95% of the time. It's 95% accuracy, but is that good? No, because it was able to predict like when the fraud actually happened. Same thing first. The model is really trash at predicting when the person left. And if you think about a business sense, if you're running a business, would you be more interested in knowing the people who are going to leave or the people who are going to stay? You're going to be more interested in kind of stopping the people who are going to leave. So lucky for us, random forest gives us a really easy way in this class to deal with this class imbalance, right? So what we're going to do is we're going to just copy this again so you can juxtapose and paste it right over here. And what we're going to do over here, we're going to give it something called class weights when we're training it. So class 0 means the person did not leave, 0.80. Class 1 means the person left. I'm going to give it 2.6. All right, so what's happening here, right? So what's happening here is both of my classes start with equal weight. My model doesn't know any better. It just knows there's 2 classes, right? And it's going to start with equal weight. It's going to be like they're equally important for me to start training. But before the model does that, I'm going to tell it. listen, the class that the people did not leave, its importance, I'm going to reduce by 20% if you think about that, proportion-wise. It started at 1. I'm going to say, no, it's not as important. It's just give it only, like it's only 0.8, like 80% of its importance, right? In a very crude way. That's what I'm trying to say. And class 1, which is basically the people who left, I'm going to blow it up. From 1, I'm going to be like, it's 2.6 times more important for you. I'm going to tell this to the model. And, okay, and then when I train the model.
Where do you get these are very specific numbers. Where do you get
Okay, again. So there is no way for you to cross-validate this because you can't just, your model does not, the cross-validation only works for overall accuracy, right? So your model doesn't know you're looking to increase the accuracy for one value of the variable, right? This is trial and error. You start with it. Okay, don't blow it up to 100. Don't blow it to 200%, 200 times. I'll just, just think about it. Everybody starts with proportion 1, reduce the proportion, go 90, 80, and increase the other one. From 1, go 1.2, 1.3. So when I do that, look at my confusion matrix. It's beautiful. Right? The diagonals are really dark, just the way I want it to. Now, there's a trade-off. Giving class weights will never increase your overall accuracy. In fact, it'll actually make it go down. So your overall accuracy is 75% versus 79%. But that's a very small drop in the fact that your true positive rate, you have 75% accuracy for predicting the people who left over 45% accuracy. By giving class weights, I was able to increase the accuracy 30%. Right? So this is a trade-off. Again, from a very objective way, this does not make sense because my accuracy decreased. But in a business sense, I want to be able to predict the person who leaves accurately, right? So what happened when I did that was we have the similar proportions now. Right? So this is the trade-off we gave. So we basically told the model, so now there must have been a lot of instances that our model predicted as not leaving because, but now I predicted they're leaving because I gave that class more weight when it was training. And because I did that, I got equal proportions. And I was able to this is a much better model, even though the accuracy over here is less than that one, because their stratified accuracy, is what this is called, is much better. Right? And this is something that you have to be very careful of. That is why, for classification, just looking at the overall accuracy can be very misleading. It's often not the best metric. You from a business sense, you really want to go in and see what your model is getting good at. Like I said, 79% accuracy, 91% accuracy for, again, so you see the 91% accuracy for predicting people who did not leave also reduced because it's a trade-off. Like I said, overall accuracy will not increase when I do this. It'll be a trade-off. Which one I'm giving more weight to.
Okay, so the upper left corner, the true...
Yeah, the diagonals are actually retained, predicted retained, and the lower one is actually churned and predicted churned. So the diagonals are what you want to have good proportions in, and this is what you want to have light proportion. So this diagonal is the value was actually retained, but our model predicted churn. So this is basically a false positive. You want this to be lower. This is a false negative. This is a true true negative, true negative, and true positive. So you want those to be higher, right? It's right over here. True positive 75%, true negative 75%.
Okay.
So yeah, so this is important. First place.
They're both 75%.
That's a good thing. You can maybe go higher. You can maybe use say like I just want to like tip it in the favor of like the other.
Is it possible to find a compromise where both true positive, true negative are higher than 75%?
But this exact model, these parameters, no. You're gonna have to go for a different model. And now, so the way I took care of this problem is I got lucky because random forwards gave me a way to deal with this inside the model, right? Usually, how you deal with class imbalance is you do different things. You usually need to do like some kind of, you need to sample again. So let's say you have 5 values positive and 95 values in your class negative, right? You're gonna oversample the positive values. So you do oversampling and undersampling. Like, so there's something called boosting. So there's gradient boosting for scikit-learn. If I was using scikit-learn gradient boosting, it does not give me the option of the class weights. So it's going to run into this problem, and I will not be able to solve it just by passing it an argument. In that case, and boosting is usually like a better algorithm, right? But in that case, I'm going to have to start by kind of like resampling my data set to be able to give it, right? So I can undersample the majority class. I can not give it all the majority classes, right?
What do you mean by undersampling?
So let's say I have 40% minority class, 60% majority class. I only give it 40% of the value. So I'm reducing my data set essentially by kind of like matching proportions. That's what I'm undersampling the majority class. I'm not giving it all the values, so it doesn't tip. Yeah.
So what we really care about is churn in this case.
Yes, in this case, we really care about churn because doesn't it make sense from a business sense? Like you want to know the people who are leaving over the people who are not leaving. Okay, this person is not leaving. Cool.
So you're saying we can oversample the number of churns.
Yeah, we can oversample the number of churn. That's more complicated. I'm not going to go into that because undersampling is usually easier than oversampling. Oversampling has to be done before you cross-validate. I really don't want to go into that. It's a little more complicated. So, so undersampling usually works better, and if you have a way to put in a class weight in your model, that's also great. Right. And another way to deal with this problem is also
Sorry, this is called the confusion matrix?
This is called the confusion matrix. You can Google that, and there's like very, very good explanations for this, right? Like I didn't get it out of a book. I got it from like different blogs I read. It's like you can find a lot of good material explaining a confusion matrix for you very well. So another thing that I also want you to know is that when my model says the person is going to leave or not leave, that's not the only thing it outputs. It also outputs their probability. So let's say leave with their probability 60%, leave with their probability 90%. So and usually the threshold is at 50%, right? So let's say I have person A, and the model says 60% leave, 40% not leave, so leave, because the majority class is 60%, right? So another way to deal with this class imbalance is you reduce that threshold. You say that if a person has more than 30% probability of leaving, you will say they're leaving, even though that's not the majority probability. 70% says they're not leaving, but I want to reduce that threshold. So I can give it more like leeway to leave. Even 30% leaving means they're leaving. I want to classify them as leaving. So that's another way you can kind of deal with this problem of like predictions. So there's just a bunch of different ways. Again, it's really hard to like cover all of them, but I'm just like if you kind of like read or like kind of go into literature or just like online, there's a lot of materials. Kind of like dealing with imbalanced classes is just they've been doing it for a very long time. There's some really, really good methods that exist for it.
How do we know that 75%
is good?
Yeah.
Again, no answer for that business problem. If your boss thinks it's good, it's good. If you're able to save a certain amount of money, it's good, right? So this is a very how is 75% good? It depends on your application. What are you trying to do with it? Okay, let me give you an example, right? Let's say an 80% accuracy that a person is going to buy your car or not is good if you think about it.
Yeah.
What about 80% accuracy a person is going to die or not? Is it better than that or worse than that if you compare those two problems? A little worse, I guess, right? You want to be a little more sure the person is going to die or not. So for the same accuracy, different problems, you can have different implications. This is a very subjective question. Is it good or not? If you're in a competition, then it's good as long as it's better than everybody else. So
I guess the only way to know is try other methods? And then just
Only way you know 75% is good when you apply it and see what happens. Like again, if it is 75%, are you able to save that company a lot of money?
Now, what about the question of, so there's a big debate about
Huh?
applying deep learning techniques to some problems.
Yeah, deep learning techniques are a good way to do that. But unfortunately, with 7,000 observations, you're better off not applying deep learning.
Yeah, so why is it then that with a supervised learning problem that deep learning would or would not be?
Deep learning problem has their own set of problems. Deep learning problem usually needs a lot of data. So the biggest problem is that to have a neural network function better, you usually need a lot more data than you would need for a model like this.
How many data tokens do we have here?
How many? I have 7,000 observations.
7,000.
That's not really good for a deep learning model.
You
That's,
want to go really big data.
yeah, you want to go bigger than that, definitely, right? But again, there is no one answer for this. Maybe you apply deep learning and it does a lot better. I don't know. But in general, I'm talking. Anything I talk about is in general, right? I still like. There's no one combination of parameters that work for everything. There's no one model that works for every problem. It's very empirical. So you're gonna have to hit and try and you see what works.
Are there other ensemble methods that you think might have done?
Yeah, boosting, but
Gradient
gradient boosting, stochastic gradient boosting. I didn't do it because I didn't have a way to resample the data set without. It'll take a lot of time. Like I will have to start by resampling it, and that takes a lot of time. So that's why I didn't want to cover it over here. But if you want to, yeah, you can go back. Just Google how to resample it in Python. Pretty easy. I'm sure there's a library for that. And then apply add a boost. You might do better than this.
So all the techniques that we did today, at least in terms of, they're all from scikit-learn?
They're all from scikit-learn. And the visualizations are from Seaborn.
Seaborn?
Yeah, Seaborn library.
That was a, what do you call that?
Yeah, it's a violin plot. It's called a violin plot.
A violin plot.
Yeah. Looks like it, doesn't it? It's called a violin plot. And yeah, and this one is just a stacked bar graph.
The violin plot was of everything they looked at.
Sorry?
You have to explain this to like some idiot business.
Yeah, you just say that they're distributed differently because you can see that
You
the
want to show
peaks,
them
right?
the violin plot.
You can see that. Okay, so just by looking at it, you can see that they're not symmetric, are they? They're different. Like this side and that side. So that's how you really explain it. So I mean, yeah. So you can see the peak over here is the peak. It peaks like in a lower value. This kind of has like a bimodal. Like you can see, like this it peaks at a higher value. So distributed differently.
So this is what we looked at before we used any machine learning.
So just okay. So in a way, knowing this in this situation didn't make it any better or worse for you. But in a business sense, like just knowing how you Rails distributed can't help you. Like it can just like I said, can you look at the data set just like it is, like over here, and tell me and kind of like can you look at this just like this is and tell me the information and tell me you got the same information as you got from the plot. That's it. You need a way to visualize your data to understand how it is distributed. In certain situations, it can be helpful or not helpful.
Okay, so we.
I mean, yeah. I mean, again, so this is like a quick view. If you want to tell someone like a quick overview of what this is about, you do that. Again, there's a lot of tutorials.
It seems like just with that first plot, we already have a pretty good intuition as to
Yeah.
who leaves, who stays, and why.
Yeah.
They leave because there's a better price available, and when they leave, it tends to be relatively early on.
Basically, yeah, you can see how those are distributed. So yeah, again, so
So that's why visual data visualization exists, right? It's like that's why you want to do it.